In an experimental department tucked inside a hardware company in New Britain, Connecticut, in 1911, 7 men are working an entire day to produce 150 ball bearings. 7 men, 1 day, 150. Do the arithmetic, and it comes out to roughly 21 bearings per man per shift, which is to say that each of these bearings represents most of an hour of a skilled man's working life. They are not being careless, and they are not being slow. They are doing something extraordinarily difficult that almost nobody in the United States knows how to do properly, and they are doing it badly, because the knowledge of how to do it well is 4,000 miles away in a small city in Bavaria, and its owners are not sharing. 32 years later, in the same city, in a factory covering 600,000 square feet in the middle of downtown New Britain, 7,000 people are producing ball bearings at a rate of 100 every minute. 100 a minute is 6,000 an hour, is 144,000 in a day of continuous running. Set that against the 7 men and their 150, and you are looking at roughly a 1,000-fold increase in a single lifetime, in the same town, under the same company name. That company was the Fafnir Bearing Company, and it was founded on a proposition that in 1911 sounded close to absurd, that an American factory could make a ball bearing as good as a German one, because in 1911 it could not. America built more automobiles than anyone on earth, and could not make the bearings that went inside them. The bearings, or the components to assemble them, came in on ships from England and above all from Germany, where they were expensive and hard to obtain and unquestionably the best in the world. This is the story of the object that America could not make, of why it was so much harder than it looks, and of how a hardware town in Connecticut learned the trick. To understand the dependency, you have to understand how completely the ball bearing had become the connective tissue of industrial civilization by the early 20th century. Anything that rotates has a bearing at each end. The bicycle boom of the 1890s ran on ball bearings. The automobile, arriving in earnest in the first decade of the new century, consumed them by the dozen per vehicle. Electric motors, machine tool spindles, generators, pumps, fans, transmissions, every rotating shaft in every machine in the world sat in bearings, and the best of those bearings were rolling element bearings, and the best rolling element bearings came out of Germany. The American position was genuinely uncomfortable. This was not a nation short of engineering talent or manufacturing capacity. This was the country that had invented interchangeable manufacture, that was in the process of inventing the moving assembly line, that would shortly be producing automobiles at a rate the rest of the world could not comprehend. And it was importing the little steel spheres that made those automobiles' wheels turn, or importing the components and assembling them domestically, because the process knowledge required to make a precision ball bearing to German standard did not exist in the United States and could not be bought. That last point is the crucial one. Patents can be licensed, machines can be purchased. But what Germany possessed was not principally a patent or a machine, it was 3 decades of accumulated, hard-won, hands-on process knowledge about a manufacturing problem that is far, far harder than it appears from the outside. And process knowledge does not travel. It lives in the hands of the men who have made the mistakes. You cannot import it. You can only, painfully, over years, grow your own, which is prescriptive lessons in all of manufacturing. Complexity of design and difficulty of production are 2 entirely different axes, and they frequently point in opposite directions. A complicated machine is hard to design and, once designed, often straightforward to make, because it is assembled from many parts, each of which is individually undemanding. A ball bearing is trivial to design and savagely hard to make, because its entire function depends on a handful of dimensions being correct to a degree of precision that ordinary manufacturing simply cannot reach, and because one of those requirements is the production, in millions, of an object that is genuinely, mathematically perfect. The resolution of the paradox is that Germany's advantage was never intellectual, it was procedural. Germany had figured out how to make a perfect sphere, cheaply, by the million, and America had not, and no amount of American cleverness about engines or assembly lines substituted for that one specific piece of shop floor know-how. To see why it was so hard, you have to look at what a ball bearing actually does, and then at what that demands of the balls inside it. The popular history of American industrial power tends to start with the assembly line and run forward, as though American manufacturing supremacy were a natural condition that simply switched on around 1913. It skips the long, unglamorous apprenticeship, the decades in which American industry was in some areas a follower, buying its precision from Europe and, slowly, expensively, learning to make it at home. It also, when it does mention ball bearings, almost always jumps straight to the Second World War and the bombing of Schweinfurt, the famous and famously costly attempt to strangle German war production by destroying its bearing plants. That story is worth telling, and this channel has told it. But it is the last chapter, and telling only the last chapter makes it look as though bearings mattered because bombers attacked them. They mattered long before, and the reason Schweinfurt was a target at all in 1943 traces back to a decision a Bavarian metalworker made in the 1880s that gave one small city a grip on a global industry. And the popular history entirely omits the mechanical heart of the matter, which is the genuinely beautiful question of how you make a perfect sphere. Not a nearly round lump, a sphere, round to within a fraction of a thousandth of an inch, identical to its neighbors, produced not one at a time by a craftsman, but in industrial millions. That is the actual problem. Everything else in the story of the ball bearing, the German dominance, the American dependency, the Connecticut factory that broke it, is downstream of that single manufacturing question. So let us answer it properly, starting with why sphericity matters so much in the first place. Put a shaft in a plain hole and turn it, and the two surfaces slide against one another. Sliding friction is high, it generates heat, and without a well-designed film of lubricant between them, the surfaces will gall and seize. The ball bearing eliminates the sliding entirely by inserting rolling elements between the shaft and its housing, and rolling friction is a small fraction of sliding friction. That is the entire proposition. Replace sliding with rolling, and the shaft spins nearly free. But look closely at how the load actually travels through the bearing, because this is where the precision requirement comes from. The shaft's weight and working load pass into the inner ring, then into the balls, then into the outer ring, then into the housing. And the contact between a ball and a raceway is, in the pure geometric sense, a single point. Under load, the steel deforms elastically, and that point spreads into a tiny ellipse, but it remains extraordinarily small, and the entire load passes through it. The pressures at that contact are enormous, far beyond what the steel could bear over any larger area, sustained only because the contact is momentary and rolling, and the steel is exceptionally hard. Now consider what happens if the balls are not all the same size. Suppose one ball in a set is 1/10,000th of an inch larger than the others. That ball, being fractionally taller, does not share the load. It carries it, all of it, or nearly. Every other ball is riding free, and the one oversized ball is taking the whole load through its single tiny contact patch at a pressure it was never designed to survive. It will fatigue, spall, and disintegrate, and its fragments will destroy everything else in the bearing. That is why the ball bearing is a precision object rather than a simple one. It does not merely need round balls, it needs balls that are round and identical to tolerances that a 19th century workshop could not measure, let alone produce. Stop and consider the sphere as a manufacturing problem because it is unlike anything else in a machine shop. Almost every other shape is made by controlling a tool's position relative to the work. You turn a cylinder by holding a cutter at a fixed distance from a rotating axis. You mill a flat by running a cutter along a straight path. You drill a hole by guiding a drill along a line. In every case, accuracy comes from accurately positioning the tool. A sphere defeats this. A sphere has no axis, no flat, no edge, no feature to reference from. Every point on its surface is identical to every other. There is no orientation in which you can clamp it, that distinguishes one part from another, and if you were to hold it and machine one region, you would need to release it, reorient it perfectly, and machine the next region, blending seamlessly, and you would have to do this over the entire surface without ever creating a facet, a step, or a flat spot. Doing that once by hand with enormous skill is possible. Doing it a million times identically is not. Before Germany solved it, this is exactly how balls were made. They were produced by hand on turning machines, largely in England, and the results were what you would expect: imprecise, prone to breakage in service, and expensive. Every bearing was limited by its worst ball, and there were always worst balls. The bicycle makers and early machine builders lived with it because there was no alternative. The breakthrough, when it came, did not consist of finding a cleverer way to aim a tool at a sphere. It consisted of abandoning the idea of aiming altogether, and it came out of a bicycle workshop in Bavaria. Friedrich Fischer was a metal worker and turner in the small Bavarian city of Schweinfurt, and in the early 1880s he was building bicycles. Bicycles need bearings, bearings need balls, and the hand-turned English balls available to him were expensive and unreliable. So he began experimenting with machines of his own design to make them. And after a long, costly, laborious series of trials, in 1883, he succeeded. His machine has come down to us as the ball-grinding mill, and what it achieved was the mass production of hardened steel balls that were of equal size and genuinely round to a precision on the order of 0.02 of a millimeter, which in the context of 1883 was astonishing. Not one ball, large volumes of balls, all alike. Fischer had turned the sphere from a craftsman's triumph into an industrial commodity, and in doing so, he founded an industry. The consequences compounded with remarkable speed. Fischer's own operations and those that grew around him made Schweinfurt the world capital of the rolling bearing. His son founded the Kugel-Fischer firm in 1906, which became the cornerstone of the German industry, and other firms clustered in the same city, drawn by the pool of skilled men and accumulated technique. By the mid-20th century, 5 plants in Schweinfurt were producing something close to 2/3 of all Germany's ball and roller bearings, and the population of the town had tripled to 50,000 on the strength of it. A single mechanic's invention in a bicycle shop had created a concentration of industrial capability so significant that 60 years later, air forces would fly across a continent and lose hundreds of aircraft trying to destroy it. And in 1911 in Connecticut, 7 men were trying to work out how he had done it. New Britain, Connecticut called itself the hardware capital, and it had earned the name. It was a town of metal-working firms, of tool and diamond, of factories that made locks and fittings and stampings and the countless small metal objects of American domestic life. It had, in other words, exactly the kind of dense local concentration of metalworking skill that any hard manufacturing problem requires, and it had one man looking for a problem worth solving. Howard Stanley Hart was president of the Hart and Cooley Company and had just come off overseeing production of the Corbin motor car. He was not an immigrant genius or a lone inventor. He was a New England manufacturer of the practical, well-connected sort. And what he possessed was an eye for a market gap and the nerve to walk into it. He looked at the American bearing situation, at a growing automobile industry buying its bearings from Germany and England at high prices and uncertain supply, and he asked the direct commercial question: could German-quality ball bearings be produced in America? Nobody in America knew the answer because nobody had seriously tried at that quality level. So Hart did what a manufacturer does. He set up an experimental department inside Hart and Cooley and began finding out. On the 8th of March, 1911, the Fafnir Bearing Company was incorporated out of that effort, taking its name from the dragon of Norse legend that coiled itself around a hoard of treasure, which is either a comment on the German grip on the industry or simply a good name for a company that intended to be formidable. And the early results were the 150 bearings a day that opened this story. That was the starting position, a small American company in a hardware town attempting to reproduce from first principles a body of process knowledge that Germany had been accumulating since 1883. So, how is it actually done? The process that Fischer pioneered and that Fafnir had to reconstruct is, in its essentials, still the process used today, and it is one of the most satisfying manufacturing sequences in all of engineering because each stage solves a specific problem created by the last. It begins with wire. Steel is drawn down to a wire of carefully controlled diameter, and this is where the first hidden requirement appears. The steel itself must be exceptionally clean. Rolling bearing steel is a through-hardening high-carbon chromium alloy, and the enemy is inclusions, microscopic non-metallic particles trapped in the metal during steelmaking. Under the punishing repeated contact stresses inside a working bearing, an inclusion just below the surface becomes the nucleus of a crack, and the crack becomes a spall, and the spall destroys the bearing. Bearing steel is therefore among the most demanding steel specifications in ordinary industry, and metallurgy that would be perfectly acceptable for a structural bolt is disqualifying here. The wire feeds into a cold heading machine which shears off a cylindrical slug of precisely the right volume, and in a single blow between two hemispherical die halves forges it cold into a rough ball. This is done at room temperature and at high speed, on the order of a ball a second for larger sizes, and several a second for smaller ones, and it is a violent and extremely loud operation. Because the die must fill completely, a slight excess of material is used, and that excess squeezes out at the parting line, leaving each rough ball wearing a ring of flash around its equator, like the seam on a poorly made toy. At this stage the ball is soft, approximately spherical, and wrong in every dimension that matters. Everything after this is the removal of error. The flash must come off, and the way it comes off contains the entire secret of sphere making, so it is worth watching closely. The rough balls are fed between two heavy plates, cast iron, faced with circular grooves. One plate is stationary and one rotates. The balls are held in the grooves under pressure and rolled around and around, and as they roll, the flash is worn away. Then the balls are collected at the outlet, returned to the inlet by a conveyor, and sent through again. And again, and again, circulating through the machine repeatedly until the desired condition is reached. Here is the crucial thing, and it is genuinely beautiful. Because a ball rolling in a groove is completely free to rotate about any axis, and because it is knocked into a new orientation every time it is discharged and recirculated, no part of any ball's surface is favored. Over thousands of passes, every region of every ball spends, statistically, exactly as much time in contact with the abrasive as every other region. The high spots projecting further are pressed harder and worn faster. The low spots are touched less. The process is therefore self-correcting, and it converges inexorably on the only shape that has no high spots and no low spots at all. That shape is the sphere. This is why you cannot make a ball by aiming at it. You make a ball by setting up a process that is blind to orientation and letting it run, and sphericity emerges as the mathematical attractor of the operation. It is a generative process rather than a positional one, and once you grasp it, the whole thing snaps into focus. Fischer's genius in 1883 was not a clever cutting geometry, but the realization that a randomizing, recirculating, orientation-blind process would produce perfect spheres in bulk from imperfect ones without any operator ever deciding where to cut. With the flash gone and the balls approximately round, they go to heat treatment, and the placement of this step in the sequence is itself a piece of hard-won process wisdom. The balls are heated to austenitising temperature, then quenched rapidly, usually in oil, transforming the steel structure into martensite, which is extremely hard and extremely brittle. They are then tempered, reheated to a lower temperature, which sacrifices a little hardness to buy back toughness and relieve the internal stresses left by the quench. The result is a ball hard enough to survive those punishing point contacts without permanently deforming, and tough enough not to shatter under shock. But hardening warps things. The volume change as the steel transforms, combined with the fierce thermal gradients of the quench, means that every ball comes out of heat treatment slightly distorted and slightly the wrong size. The sphericity so carefully generated before hardening has been partially spoiled by the hardening itself, which is exactly why the work is not finished before heat treatment. The sequence is deliberate. Rough the balls while the steel is soft and easy to cut, because removing large amounts of material from hardened steel is slow and expensive. Then harden. Then grind again, now on hardened steel, to restore and improve the geometry that hardening disturbed. Grinding after heat treatment uses the same principle as before, the balls rolling in grooves between a plate and an abrasive wheel, circulating repeatedly, the same orientation blind convergence, but now working on steel hard enough to hold the shape it is given. Do it in the wrong order, and you either wear out your tooling on hardened steel or you deliver perfectly round balls that warp in the furnace. Knowing the order is not obvious. It is precisely the sort of thing that is learned by failing, and it is precisely the sort of thing that does not cross an ocean in a book. The final operation is lapping, and it is the same idea again, taken to its extreme. The balls are rolled once more between plates, one fixed, one rotating slowly, but now the abrasive is exceptionally fine, a slurry of very fine grit or diamond dust, and the material removal rate is minute. Lapping is not shaping. It is the last correction, taking the balls from very good to as measurement can confirm. The surfaces come out with a mirror finish, and the geometry converges to diameter variations well below a micron and sphericity to match. Then the balls are washed to remove every trace of abrasive and fluid, because a single embedded grain of lapping compound left on a bearing ball is a guarantee of eventual failure. They are inspected for scratches and defects, and then they are sorted and graded, because even after all of this, small variations remain. And the whole point is that the balls in one bearing must match each other. The grading system that grew up around this expresses precision as a grade number, lower being tighter, and it encompasses diameter tolerance, sphericity, and surface finish together. Note what the sorting implies. Even the best process does not produce identical balls. It produces a population with a distribution, and the final act of precision is measurement and selection, putting matched balls together and sending the rest to less demanding grades. Precision at this level is not only a matter of making well, it is a matter of measuring well, and then choosing. 7 men producing 150 bearings a day were fighting every one of these stages simultaneously, with none of the accumulated shortcuts, and every one of those stages had to be solved before the 8th man could be hired. The balls are only half the problem. The rings they roll in are the other half, and they contain a subtlety that repays attention. Instinct says that the groove in the raceway should match the ball exactly, cradling it. Instinct is wrong, and dangerously so. If the groove radius equaled the ball radius, the ball would contact the raceway along a broad curved band, rather than at a point. And because different parts of that band would sit at different distances from the bearing's axis, they would need to travel at different speeds. They cannot, it is one rigid ball. So most of the contact band would have to slide rather than roll, which reintroduces exactly the sliding friction the bearing exists to eliminate, generating heat and wear, and destroying the bearing's whole purpose. So the groove is deliberately made a little larger in radius than the ball, conventionally a modest percentage larger, which shrinks the contact back down to something very close to a point. That restores true rolling. But it also concentrates the load into a tiny ellipse, which drives the contact pressure up and demands the hardness and the metallurgical cleanliness discussed earlier. The groove radius is therefore a compromise between friction and stress, and where a manufacturer sets it is a matter of judgment, backed by testing, another piece of proprietary process knowledge. And the raceways themselves must be ground, hardened, and finished to the same order of precision as the balls on the inside of a ring, which is a substantially more awkward machining problem than the outside of one. Bearing quality is the product of ball quality and raceway quality together, and a company that had mastered only one of them had mastered nothing. There is one more problem, and it is the kind that delights anyone who likes a puzzle. Consider the deep groove ball bearing, the most common type ever made, in which the balls sit in grooves cut into both the inner and outer rings, so that the bearing can carry load along the shaft as well as across it. The grooves are deep, which is what makes the bearing strong. Now assemble it. The inner ring must go inside the outer ring, with balls between them, and the balls must be larger than the radial gap, because if they were not, they would fall out and carry nothing. So how do the balls get in? The answer, patented at the beginning of the 20th century and known ever since as the Conrad method after the engineer credited with it, is elegant enough to be worth picturing. You place the inner ring inside the outer ring, but push it hard to one side, so the two rings are eccentric, touching on one side and leaving a crescent-shaped gap on the other. Into that crescent you drop the balls, one after another, as many as will fit, which is fewer than the bearing will finally hold in the sense of filling the circumference. Then you push the inner ring back to the center, which traps the balls, and finally you distribute the balls evenly around the circumference and install a cage to hold them at their spacing. No slots, no split rings, no assembly features to weaken the raceways, just a sequence of moves, exploiting the clearance that exists only during assembly. It is the sort of solution that seems obvious once seen and is invisible before, and it is another example of why the ball bearing is not the simple object it appears. Even putting it together required an invention. The cage, or separator, looks like the least important part of a bearing and is in fact essential, for a reason that is easy to miss. Watch two adjacent balls rolling between the raceways. Both are rotating in the same rotational sense as they roll along. But at the point where their surfaces come closest to one another, the surface of one ball is moving in one direction and the surface of the other is moving in the opposite direction. Because that is what happens when two adjacent rotating bodies touch. Their surfaces meet head-on at twice the surface speed. If the balls were free to bunch up and touch, every such contact would be a high-speed rubbing contact, sliding rather than rolling, generating heat, wearing flats, and defeating the purpose of the whole device. So the cage holds each ball in its own pocket, keeps the spacing, and guarantees that the only contacts in the bearing are the rolling contacts with the raceways. It carries almost no load. It simply enforces the geometry. This is a recurring theme in the whole subject and worth naming. A ball bearing is not a device that works because its parts are strong. It is a device that works because its geometry is exactly right, and nearly every component in it exists to preserve a geometric condition rather than to carry a force. The balls must be identical so that load is shared. The groove must be oversized so that contact stays a point. The cage must be present so that balls never rub. Get the geometry right, and a few grams of steel will carry astonishing loads for millions of revolutions. Get it slightly wrong, and the same steel destroys itself in an afternoon. For its first years, Fafnir's project was reproduction, learn to do, in New Britain, what Schweinfurt already did. That is an unglamorous ambition, and it is the correct one, because you cannot innovate past a competitor whose baseline you have not yet reached. But something happens when a company finally reaches the baseline. It stops looking at what the leader does and starts looking at what the customer needs. And the moment Fafnir got there, it began producing inventions of its own. Before 1925, the company had introduced the wide inner ring bearing, the pillow block, the self-aligning pillow block, and the self-locking collar, and the pillow block and the self-locking collar became industry standards. These are not exotic devices, and that is the point. A pillow block is a housing that holds a bearing so that a shaft can simply be bolted to a frame, complete with mounting feet, instead of requiring a machined bore in a casting. A self-aligning pillow block adds the ability to accommodate small misalignments between two supports, which in real machinery is always present and always destructive. A self-locking collar is a means of clamping the bearing's inner ring onto a plain shaft without machining a shoulder or a keyway. Every one of these makes the bearing easier to use for the ordinary engineer building ordinary machinery, and that is a characteristically American axis of innovation. Germany had made the bearing excellent. Fafnir set about making it convenient, and convenience, applied across a whole economy of machine builders, sells enormous numbers of bearings. Within a generation, the follower had found ground of its own to lead on. Then came the war, and the industry that had been built out of commercial ambition became strategic infrastructure overnight. Every aircraft engine, every supercharger, every gun turret traverse, every tank transmission, every electric motor in every ship, every machine tool in every factory building, any of those things, all of it turned on bearings. Demand went vertical, and Fafnir, which had spent 3 decades climbing from 150 bearings a day to a serious industrial operation, expanded into something that would have been unrecognizable to the 7 men in the experimental department, 7,000 workers in a 600,000 square foot plant in the center of New Britain, turning out 100 ball bearings every minute. The workforce that achieved that number is worth pausing on, because it was not the workforce of 1911. In June of 1943, the photographer Gordon Parks came to the plant on assignment and photographed the people making these bearings, and the record he left is a portrait of exactly what American war manufacturing actually looked like. Among his subjects was Joseph Koilnik, described as a Russian Jewish immigrant working as a hammerman on a forging crew. Immigrants, women, men from farms and shops, the entire available population of a country at war, doing precision work at industrial pace. They could do it for the same reason the Jeep line ran at a Jeep every 90 seconds, and the same reason a shell fuse could be assembled by someone who had never seen a factory in January. The skill had been moved off the operator and into the process. The recirculating grinders, the graded plates, the gauges, the sorting, all of it was set up once by people who understood it deeply, and thereafter it produced spheres, whether or not the person feeding it understood why. By 1946, Fafnir was the largest independent ball bearing manufacturer in the United States, exporting to Canada, Latin America, Europe, Africa, the Middle East, Asia, and the South Pacific. The dependency had not merely been broken, it had been reversed. And what of Schweinfurt, the town whose mechanic had started all of this? The concentration that had made Schweinfurt so formidable made it, in the end, the most obvious target in Germany. 5 plants in one small city, producing something near 2/3 of a nation's ball and roller bearings, in an economy where the aviation industry alone consumed something on the order of 2.5 million bearings a month. Allied planners looked at that and saw a bottleneck, a single point through which the entire German war machine passed, and in 1943 they went for it, at a cost in bombers and crews that remains among the heaviest of the war. The results were disappointing relative to the price, for reasons this channel has explored elsewhere. Stockpiles, dispersal, neutral suppliers, substitution, and the general truth that an industry is more resilient than a set of buildings. But the strategic observation stands, and it is the mirror image of everything in this story. Germany's bearing industry was superb and concentrated. America's was, by the 1940s, superb and spread across many firms in many states, Fafnir in Connecticut being the largest independent among a whole population of competitors. Germany had a capital city of bearings. America had an industry with no capital at all. That is not a claim of American cleverness. It is largely an accident of how the two industries grew, one from a single inventor's workshop outward, the other from a scatter of firms all trying to displace imports at once. But the strategic consequence was real, and the lesson generalizes well beyond bearings. The thing that makes you dominant in peacetime, the deep concentration of skill in one place, is the thing that makes you vulnerable in war. Excellence and resilience are not the same property, and they can be in tension. Honesty requires a correction to the title, and the correction makes the story better rather than worse. Fafnir was not the only factory. It was not even the first. New Departure in Bristol, Connecticut, had been making ball bearings since the 1890s, having started, improbably, as a doorbell company, and had patented bearing designs of its own by 1908, before becoming part of General Motors. Hyatt Roller Bearing, Norma Hoffman, Marlin Rockwell, and the American operations of SKF all built the industry alongside Fafnir, and Timken had been making its tapered roller bearings since 1899. The American bearing industry was a crowd, not a hero, nor was Germany the only source of imports. Bearings and components came from England as well, and the greatest single force in the world bearing industry was Swedish, not German. And Britain faced precisely the same dependency at precisely the same time, founding firms such as Ransom and Marles during the First World War for exactly the same reason. Before the war, most British bearings had been imported, chiefly from Germany. So the accurate version is this. Around 1911, the best bearings in the world came from Germany, America could not match them, and a number of American firms set out to change that. Fafnir is the clearest and best documented example of a company founded explicitly on the proposition of making German quality bearings in America. It started from an almost comically weak position, and it ended as the largest independent ball bearing manufacturer in the country. That is a smaller claim than the title makes, and a more impressive one, because it is true. The lesson of the ball bearing is about the difference between knowing and doing. Every engineer in America in 1911 knew what a ball bearing was, could draw one, could explain exactly why it worked. Not one of them could make one to German standard, and the gap between those two states is where industrial power actually lives. Design knowledge is published, portable, and cheap. Process knowledge is tacit, local, and expensive, accumulated only by making the thing badly for long enough to learn how to make it well, and it is the only kind that cannot be acquired by reading. Which means that closing such a gap is never a matter of a breakthrough. It is a matter of a company being willing to spend years being worse than the competition on purpose. 7 men, 1 day, 150 bearings is what the beginning of that always looks like, and it looks like failure. And the only difference between a firm that becomes an industry and a firm that quits is whether anyone is prepared to fund the humiliating part. In a war decided by what could be made, the smallest and simplest object in the machine was one of the hardest to make, and America started from behind. The perfect sphere cannot be cut because there is no place on it to aim. It can only be generated by rolling imperfect balls endlessly between grooved plates until every high spot has been worn away, and the only shape left is the one with no high spots at all. Friedrich Fischer understood that in a Bavarian bicycle shop in 1883, and it made his town the capital of an industry. 28 years later, 7 men in a Connecticut hardware town began working it out for themselves, badly, expensively, 150 at a time. 32 years after that, the same company was making 100 a minute in a plant with 7,000 people, supplying an arsenal that armed half the world and had gone from copying German bearings to exporting American ones to 6 continents. And the final measure of how far that convergence ran is this. Equipment made in that same New Britain factory went to the moon aboard Apollo 11. The little steel spheres America once had to buy from Bavaria, ground around by a process that works precisely because nobody aims it, ended up 240,000 miles away, still turning. That was enough. In a war decided by what could be made, they learned to make the hard, simple thing, and then they made it faster than anyone.